All right, welcome back. We were just talking about how uranium breaks down, goes through mutation, and changes into different intermediate products, which would be these: thorium, proactinium, uranium, thorium, radium, radon, polonium, actinium, bismuth, polonium, and bismuth, and eventually ends up as lead. All right, now all of these are radioactive or unstable, and therefore they continue to break down over time. And eventually you get down to lead with an atomic number of 82, and it'd be lead 206. And this is not radioactive, it is stable, and that is the end product of the uranium breaking down or transmutation. Okay? And so that's kind of generally how to do this. Now, any radioactive element will go through its own different step or progressions, depending on what the element is that you start with, if it is radioactive. Mutation, or this process of one element breaking down into other elements, happens at a fairly constant progress. And so we can measure a certain sample, for example, radium 226 here it talks about, and we know that at the rate of 1620 years, half of that radium sample will be broken down into different elements. All right, in another 1620 years, half of that would break down, and half again in 620 more years. Okay, this is called the half-life, the length of time it takes for half of a sample to break down into the next element on the chain of transmutation and the elements that it becomes. All right, now as far as we know, this is a very constant process. All right, now that assumes some things. One, that it continues at the same rate. For example, has anyone ever taken a sample of radium 226 and waited for 1600 years to see if there was exactly half of it at the end of that? No, they have not. What they can do is measure the rate at which it is breaking down and estimate at which point half of it would be broken down. All right. Same thing, for example, uranium, which has a half-life of 4.5 billion years. Okay, basically, if it continues breaking down at the rate that it breaks down in laboratories now, it would take 4.5 billion years for half of it to be gone. Okay, and have changed into lead. Now, so once again, that assumes that this is constant and that other factors don't affect it. And so far, we have not found anything that seems to affect it. Okay, once again, obviously, science is only based on what we found out so far. It's possible that there could be some things that would affect it, but so far, it seems to be fairly constant and continue. And since that, scientists use this to date things, to date objects. Okay, you've heard people talking about the date of the Earth, how old is the Earth, possibly archaeological samples, things like that. And they're using half-lives of different elements, how long it takes for half of those elements to break down. Now, in order to do that, we have to measure the amount of different types of atoms and how much radiation they're giving off at any given time. So how do we do that? Basically, to measure, we use a Geiger counter. You've probably seen them in movies where you're going around and they hear a click, 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 click sound, and it gets higher as they get close to the atomic bomb or whatever's been a nuclear weapon that's been held somewhere, or if it's at a nuclear power plant and there's a leaking, it would go faster. Basically, you have a tube of gas up here on the side of certain gas. As it's exposed to radiation, it causes basically the ticking sound, and it would increase or decrease depending on the amount of radiation present. Okay, these are called scintillation counters, and basically, as radiation comes through this, causes flashes of lights, either alpha, beta particles, or the gamma radiation causes flash of light. Is measured how often that happens, and that gives us an idea of how fast it is breaking down. And once we know how fast it's breaking down over a certain length of time, then we can estimate how long it would take for half of it to completely break down. Work around radiation, notice there's a warning back here, high radiation area. If you work around radiation on a regular basis, you're probably still going to be exposed to it, even with careful, just like x-ray technicians and so forth. Even if you try to be careful, you're still going to be possibly exposed to it. So most workers in these areas would have a type of badge on here that will either change colors or give a warning if you're exposed to a burst of radiation, or if it just accumulative. Over time, you're exposed to a little bit more, a little bit more, a little bit more, and it would give off some kind of warning that you've been exposed to enough that you need to get out. Okay, and so you would stop for the day, I guess, for the week. I don't know if that means you get the next week off or whatever, but at any rate, you would say, hey, we've got to get away. All right, and that's just to protect people who work around radiation that are not exposed to levels that are considered harmful. Okay? And these are basically just detectors of radiation, but they've been set so that at a certain level they will go off and let those people know that you've been exposed to enough, you need to get out of there. And it could also, of course, just like the old canary in a gold mine, they used to have canaries that when they're exposed to gases, they would die. If they die, it's time for the people to get out. Well, the same thing here. This kind of gives them a warning that they've been exposed to radiation before it gets to be extremely harmful levels. How is half-lives used to date things? Let's look at a common example. In the atmosphere, which is made up mostly of nitrogen, although it also contains oxygen and some other elements, but 75% of it or so is nitrogen. Cosmic rays from outer space have radiation and energy, and very often, as those energy hit atoms, they will cause protons and neutrons to be released. Okay. Now, for the protons, it's not that big a deal. The protons will go through the atmosphere until they pick up an electron from another atom somewhere along the way. Electrons are easily given up. And so it picks up that electron, and now you have one proton with one electron going around it, and basically it becomes a hydrogen atom. Okay? And so we have hydrogen, which is fairly harmless, no big deal. Okay? We don't mind having hydrogens around. But the neutrons, on the other hand, are not really harmful, but they do a little more complicated things. They can't just, since they have no charge, they're not going to react with electrons or protons, and so they will usually run into another atom, and the odds are it's going to be nitrogen, because 3/4 of the atmosphere is nitrogen. So nitrogen-14 is a normal, stable atom of nitrogen. When the neutron hits it, it will join the nitrogen atom, but it will knock off a proton particle. Okay, and when it does that, the mass does not change, but now you have one less neutron, but one more proton. So that changes from element number 7, which is nitrogen. Now you have 6 protons, because you just lost a proton. The mass is about the same, so it's still 14. So it's carbon-14. Now, the most common carbon atom is normally carbon-12. Okay, you have 6 protons, 6 neutrons, so it's carbon-12. Carbon-14 now, of course, has 6 protons, because it has to have 6 protons in order to be carbon, but it now has 8 neutrons. Okay, so it's a heavier carbon atom, if you will. And approximately 1/millionth of the 1% of carbon in our atmosphere is made up of carbon. So a very small part of those are made out of carbon-14 atoms. Now, all living things take carbon in and make it part of their bodies. Sugars, which are C6H12O6, glucose that plants make, and then we eat the plants, or eat animals that eat the plants, and so that carbon becomes in it. And there's a part of our bodies, and we have many carbon atoms in our body. All right, so basically, a certain percentage of those carbon atoms that we inhale or put into our body are basically become carbon-14. All right, and so we would expect a certain level, a certain amount of our atoms in our body to be made out of carbon-14. Now, this once again assumes some things. That one, the atmosphere has been relatively stable as it is now, and that the rate of, or the percentage of carbon in the atmosphere, carbon-14 in the atmosphere, has stayed the same. Okay, and so assuming that, then we would expect that when an animal is alive, it would have a certain level of carbon-14. Now, over time, let's just say this one died 22,000 years ago, let's say here, almost 23,000 years ago, and it dies, it has a certain level of carbon-14. But over time, these would break down. Okay, and carbon-14 basically has a half-life, okay, of approximately 5,730 years, give or take a little bit. Obviously, we're not going to be very exact here, okay, but it's about almost 6,000 years, okay? And so in about 5,000 something, almost 6,000 years, you would expect that half of that carbon-14 would be gone. In another 5,000 to 6,000 years, you would expect about half of that to be gone, and then about half of that to go. Now, technically, the carbon-14 is still present. There's always going to be a certain, if you keep halving it and halving it and halving it, there's always going to be a little bit left. But eventually it's going to get to be so small amount that we can't measure it anymore. And so generally, carbon-14 dating is good for objects that are up about 50,000 years old. After that, you're getting to where there's so much of carbon-14 left that it's not, can't measure it exact enough to be very accurate. Okay, and so you know, and there's also, like I said, these are approximates because possibly the atmosphere has changed over time. The amount of cosmic rays hitting the atmosphere causing carbon-14 to be formed could have changed over time also. Okay, this is called radiometric dating because we're using the radioactive half-lives for breaking down as these radioactive elements break down to measure how old they were. Okay, and so that's how carbon-14. Now, carbon-14 works for things that are living because they take up carbon. Other things, not so much. Now, radiometric dating is called carbon-14 dating. Radiometric dating use radioactive things such as uranium in rocks, okay, to date the Earth and to date those rocks. Okay, they have much longer half-lives. Okay, we said like uranium is about 4.5 billion. Now, part of the problem says, well, how do you know how much was there to begin with? Well, once again, you assume that there's a certain amount. In rocks, we would look at the amount of lead versus the amount of uranium and estimate how much of it has broken down over time from uranium into lead. But once again, these are estimates. Yes, they're not exact, but they give us an idea how long those rocks may have been there based on the half-lives of the radioactive elements in them. I didn't give you the pictures, but how the radioactive dating, we said that you have a neutron that hits a nitrogen atom. It converts it to a carbon-14 atom that loses a proton. Now, what eventually would happen to that, we say it breaks down, and basically what would happen is your carbon-14 atom would basically, one of the neutrons would give off an electron, beta decay, if you will. It's giving off a beta particle, and that would change one of the neutrons to a proton, and it would be changed back to nitrogen-14. Okay, and that's what we said. So basically, when we're saying that carbon-14 is breaking down, there's less of it. You would also see an increase in the nitrogen-14 that would be present in the element. Okay, now if that's released out into the air, then you may not be able to measure that, but the amount of carbon left is what we'd use to date it. Now, talking about nuclear fission, okay, and nuclear fusion, talk about one of the most important things probably about nuclear energy is, how do we get it? And radioactivity is basically the core of that. So let's talk about a little bit about fission, first of all. Fission means to split, fusion means to put together. Let's look at fission first. Fission is something we can do. Okay, and basically we said earlier there are two forces that hold the atom together. There's the strong nuclear forces that hold the nucleus together, whereas there's the electrical force, which is the protons wanting to repel each other in different directions because they're all positively charged. Okay, and normally in most atoms, the nuclear force, strong nuclear force is the stronger of the two, and it holds them together, so that's not much of a problem. But as you get larger and larger, okay, one of the very largest nuclei or atoms that naturally occur would be that of uranium, okay, which has 92 protons and about 146 neutrons. Okay, so it's getting very large, and now the strong nuclear force is not dominating anymore. Okay, and they're almost equal. Now it can hold the atom together, but if something happens to it, okay. Say, for example, a neutron hits it, or spare neutron floating around hits it, it will begin to stretch the atom out. Okay. Now, as it stretches the atom out, okay, this neutron hits it, it stretches the atom out, and that puts stress on the atom. And because of that, it's called critical deformation. It deforms the atom enough, causes it to stretch out enough that now the electrical force, all these protons that are wanting to repel each other, these the red protons, they're wanting to repel each other, it becomes the stronger force, okay? And so basically it causes the nucleus to go ahead and split, okay? The repelling of those protons, the electrical force becomes stronger, and it actually splits the atom, okay? And the result of that is usually that it sends out 3 neutrons, okay? They're given off. All right, now if that were all that happened, then it would release some energy, but not a whole lot, okay? Or at least not an uncontrollable amount, just one atom. Now, the deal is, though, once you hit 1 neutron into 1 uranium atom, it splits, but it gives off 3 neutrons. Well, what do those neutrons do? Well, they go out and they hit more uranium atoms. Each of those hit 1, and each of the atoms they hit give off 3 neutrons, which go out and hit 3 more, and now we have kind of a chain reaction going on. Okay. Now, if you have a small amount of uranium, then eventually it will never increase because there's not enough atoms to keep increasing and increasing and increasing the chain forever. However, if you have a larger amount, then it will continue to get more and more and more reactions triggered by these neutrons that are escaping.